Welcome back, everybody. So we're going to continue with a session on optic UV constraints on the interstellar medium, and we have two talks, and we'll start with Vianney Lebouteiller.
Okay, thanks. So I will present the status and some science goal of LUVOIR. As you will see, LUVOIR is a multi-wavelength observatory, but this presentation will be a UV perspective on ISM studies. And another disclaimer is that by ISM, I really mean general ISM, and I will talk about ISM tracers a lot, but a lot of things could be said about LUVOIR and protoplanetary disks, for instance, but I won't mention it too much. So for those of you who don't know, LUVOIR is the Large UV Optical Infrared Telescope. So it's one of the 4 missions proposed for the Astro 2020 Decadal Survey. It's a warm telescope and it has 2 configurations, one with 8-meter mirror and one with a 15-meter mirror. The one with the 15-meter mirror requires a new launching vehicle that doesn't exist yet. So that's something to take into account. So basically it's 2 missions in one. So it's not 4 missions that are proposed to the Decadal, but 5 if you think of it. Most of the signature science cases require a mirror around 6.7 to 8 meters. Some science goals require more than 8 meters. So that includes some solar system science cases like the habitable moons, small bodies in the solar system, but also smaller scales across cosmic times and high precision astrometry or the initial mass function. Then some science goals require more than 15 meters. So there are a few, but here I just selected 1 or 2 actually, which is tracking the ionizing light over cosmic times and multi-scale assembly of galaxies. And the limiting factor is really to be able to resolve dwarf galaxies at high redshift. In the bottom, you have the 4 instruments. So it's really 3 plus 1 because the 3 first instruments, Eclipse, the coronagraph with imaging and spectroscopy, HDI, the wide field imager, and LUMOS, the multi-object spectrograph, they are for the 8-meter version. And for the 15-meter version, you have these 3 plus Pollux, which is a CNES supported instrument. And Pollux is really specialized in point source, high spectral resolution spectroscopy, and providing polarimetry as well. So it's a spectral polarimeter. And between all these instruments, you have a wavelength range between 1,000 angstroms and 10,000 angstroms. So this is a general slide about the science goals of LUVOIR. So there are 3 pillars, cosmic origin, solar system, and exoplanets. On the left, you have, so it's a dwarf galaxy at redshift 2, and you have what Hubble can see on the top left, what ELT can see on the top right, and then you have the 2 versions of LUVOIR observing the same galaxy. So the image doesn't do justice really to the depth of the resolution of what you have, but so the improvement is significant even as compared to the ELT, and most importantly, you have UV, optical, and infrared in that image. Then for the solar system, this is on the right, you have a simulation of the UV plumes of Europa, and on the right, and on the left, this is an actual observation with Hubble. So you can see the plumes in the bottom left, and the disk was invisible to Hubble for lack of sensitivity. And so on the right, you can see that you can do, of course, much better with LUVOIR. And so here we're talking about Lyman alpha emission that comes from water dissociation at the surface. Then you have the exoplanets, and this is a simulation of stellar system at 12.5 parsecs, where you can see here Jupiter, Venus, and the Earth, how they would look like. This is with the 15-meter version here. And an important thing to notice is that you can get a spectrum for each of these planets because the Eclipse instrument is also a spectrograph. In this plot, you can see the huge sensitivity gap. So it's true for the optical and even the infrared domain. So if you think of it, LUVOIR can be seen as a super ELT or super JWST. So a lot of the science goals that ELT and JWST have are also relevant for LUVOIR. So that's why I will focus more on the UV actually. In the UV, the sensitivity gap is really dramatic as compared to Hubble COS, which is the only instrument in the UV observing as we speak in the for ISM studies in space. And I didn't show FUSE, which observed below 1,000 angstroms, but the sensitivity gap is even larger. This is how things are organized. So you have the science and technology definition team with the 3 science topics plus simulations, so cosmic origins, exoplanets, solar system, and simulations. The Pollux team is separate. So the PIs are Jean-Claude Bourret and Coraline Henner. It's separate, and I think it's because actually most of the people in that team are not American, and also it's an instrument that is proposed for the 15-meter version only, like I said. And so there are several working groups mentioned here for Pollux. The one on the ISM and IGM was actually handled by Cécile Gris right here, and I took over for around the time of the Voyage 2050 TISA white papers. And so I split that into different subcategories, but it's not really a formal separation. It's just one way to think of it, but we have people basically interested in the ISM, extragalactic ISM, polarization, and intergalactic medium, or rather I should say circumgalactic medium. So, like I said, in the optical and near infrared, you can think of LUVOIR as a super ELT and GWST. So there are a lot of things that are really relevant to the ISM. You can mention temperature fluctuations or abundance metallicity variations and weak recombination lines, etc. But I really want to focus on the UV because this is one domain that is missing right now below 1,000 angstroms, and that will be missing when HST is not active anymore, completely missing. So HST observes above 1,100 angstroms and at a resolution about 25,000, but the sensitivity decreases with time, and so it's becoming urgent to have new detectors in the UV in space. And the domain below 1,100 has been missing since FUSE, so since 2007. So it's important to gain access again to the far UV domain, and with a relatively larger effective area as compared to previous instruments, and also higher spatial and spectral resolution, which you will see is really key for ISM studies. So the LUMOS instrument is really your go-to instrument for UV spectroscopy because it has a huge field of view, high spatial resolution, and a resolution that is up to 30,000, which is not bad. Huh? And then Pollux is will be the 3rd dimension spectroscopy, so extremely high spectral resolution, more than 100,000, and providing polarimetry as well. So really LUVOIR is great for targeting individual lines of sight in the Milky Way or in external galaxies. So to do the exquisite ISM studies in the Milky Way and in nearby galaxies. And there is a huge discovery space for polarization studies with gas, polarization of gas. And these are just a couple of illustrations. So these are for the LUMOS instrument, but you can see Orion here and the LUMOS field of view in blue. And then this is a zoom on the bottom left, and you have micro shutters. So you have a bunch of them. It's 840 around along the field of view times, I don't remember how much, 400 something. And so you have micro shutters, and you can get a spectrum for each protoplanetary disks in that region. And so it's a great instrument to study these disks, but also the environment around them. So you have a spectrum for each of them. So here it's, I think, it's a simulation where you can see water absorption and H2 absorption, because the far UV is really rich in H2 transitions. This is another illustration of what you could do with LUMOS. So for several star-forming regions here, 30 Doradus in the LMC, M83, Perseus, and NGC 6814. And you have the LUMOS field of view. So I think it's like, yeah, I don't remember exactly how the configuration is defined here. On the right, you can see the small squares which define the micro shutter sizes. And so you can basically get a spectrum for each of these points. So if you want to know more about LUVOIR, of course, you have the final report, and there are also the Astro 2020 white papers. Here are listed 3 of these white papers that were written by people from the Pollux working group, ISM working group. So that are relevant for PCMI, but also there are many others that were written obviously by American colleagues. And so here I listed a few that were focused on the UV, and a lot of them are actually about the ISM as well. You have also the ESA Voyage 2050 white papers. So we have one white paper that combined the three white papers submitted for the Astro 2020. And in that white paper, we advocate for a contribution of ESA to something like LUVOIR or a new European UV telescope that could be EUVO, which I will mention in the next slide. I also mentioned another white paper, which we were not part of, but that's relevant for PCMI, for in situ investigations of the LISM. So you can have a look at that. Let's see. So just a few words on the general UV landscape. So there were 7 UV-related white papers for ESA Voyage 2050. And it's also an occasion for me to say that a lot of the community, the UV community is gathered under this network, the network for ultraviolet astrophysics. And since 2018, it was actually transformed into the IAU Division B UV Astronomy Working Group, GNUVA, which is fairly active. There are like 2 conferences every year. This group led to the proposal of EUVO, which is a UV telescope led by ESA. So it includes the 2 PIs of Pollux and Alain Le Cavalier also at IAP. Now there are several other missions that are proposed in the UV, but like I will say later, maybe they are not as well adapted to ISM studies as LUVOIR or EUVO. From the US and Canadian side, there were 65 Astro 2020 UV related white papers. A lot of them were about LUVOIR, but not only. And so on the US and Canadian side, there are a lot of several UV missions being proposed, like CITES, for instance, and a lot of them are mid-X or probe class missions, or relatively small scale, that are supposed to bridge the gap between existing UV instrumentation, existing UV telescopes like HST COS, and next generations like LUVOIR. And so to keep in mind is that most of these missions are not optimal for ISM studies because they have a spectral resolution that is not that high, and the sensitivity might not be that high either. And the 2 that stand apart are really EUVO and LUVOIR. And like I said, another thing to keep in mind is that LUVOIR is only proposed for the 15-meter of LUVOIR, 15-meter version. So if you're not familiar with the UV astronomy for the ISM, it's really an absorption method, absorption technique. So in the UV, you can study pretty much all the ISM phases, from the hot interstellar medium to the warm, neutral, and ionized medium, and cold neutral medium and molecular. And so you measure column densities of atoms, molecules, of absorption lines that are superimposed on the stellar continuum. So it can be a quasar continuum as well. And in the bottom, you see a sketch of the various configurations that you can use. So the background sources can be a quasar or a star in an external galaxy, of course, a Milky Way star, or even an unresolved cluster in an external galaxy. And the lines of sight will intersect the ISM and the CGM of an external galaxy, and the CGM and ISM of the Milky Way as well. So it's a complex spectrum at the end you get, and you need to disentangle all these lines, but it's very rich in information, of course. And so it's so rich that I will take you to a little tour of our UV tracers to explain a bit what we can see. I will try to go a little bit quickly, especially on the figures, and they are just here to illustrate. So first of all, the hydrogen is, of course, an important element. You get access to the Lyman series. So Lyman alpha at 1215, and then Lyman beta at 1025, and so on and so on. So hydrogen is very important. Of course, you can study the distribution of matter in the ISM and in the CGM. You can study the kinematics and the mass distribution of high velocity clouds and infalling gas, cosmic wave filaments, etc. And what's interesting in the UV really is that you can access very low column densities that are really difficult to reach with radio observatories. And as an illustration, column densities of 10 to the 13 are often observed in intergalactic Lyman alpha absorbers. And that's right now. So imagine with LUVOIR, we can do even better than that. So hydrogen is, of course, an important element for many reasons, but it's also a reference for chemical abundances. So you can measure self-consistently abundances in the far UV domain with the metal absorption lines that I will mention, and hydrogen. And then if you have hydrogen and H2, which you get within the far UV, you can study things like molecular gas fraction, especially in the diffuse ISM or the atomic to molecular transition. One thing to keep in mind in the far UV is that the Lyman alpha profile is complex, so it's better to get Lyman beta and above, and so you need to get below 1100 angstroms if possible. Then you get deuterium, which is really right next to the hydrogen lines. So you can measure the deuterium. So it's in absorption here, so it's quite visible. And it's important, of course, for constraints for Big Bang nucleosynthesis models. And what people measure is D/H, but because of the huge difference between the column densities of deuterium and hydrogen, people prefer to measure D/O or HD/H2 even. And what's interesting also is that you might want to target high redshift systems to mitigate astration issues because you will have a lower metallicity on average. And you might also want to study deuterium in the local ISM to study the depletion in detail and nearby galaxies also for metallicity effects. Here, what's mostly important is to get enough spectral resolution to disentangle from the hydrogen lines. So you can see you can observe the diffuse molecular gas lines also. So you have the Lyman and Werner bands. Most of the important lines are either below 1100 and below 1000 angstroms, the strongest lines. But it's not only H2 you get, you can also get absorption lines of CO, CH, and CH+, for instance. And you can also study even the CO dark molecular gas through transitions like C1 or C2 star, which is the UV notation for the fine structure level of C+. And with all of that, you can study molecular formation pathways and a bunch of things, and or the dissipation of turbulence through the H2 ladder. And like I said, here it's really important. What's really important is to access below 1100 angstroms and to also get the kinematics, as I will show a bit later. And you also want to reach as high AV line of sight as possible if you want to reach the molecular regime and not just the diffuse or translucent regime. You get a lot of ionized gas lines, with which you can study the ionization structure. So you can study things like the ionization fraction of the warm ionized medium as a function of the ionizing energy. And here you can get all these column densities as 1, 2, 3, 4, 5. So it's really powerful tool. You can also study the partly ionized neutral gas. So ions like N2 or argon2 that will be tracing the partial ionization of the neutral gas. And it's what's interesting here is that it's a really sensitive probe of the photoionization by extreme UV or soft X-ray photons, soft X-ray, sorry. You have the hot ionized gas. So FUSE has seen ubiquitous O6 emission coming from the Milky Way halo. So we're talking about 138 EVs. And you can also see N5. And the origin is still debated. It might be cooling lines for supernovae shocked gas or turbulent mixing layers or conductive interface between hot and cold gas. And one way to solve this issue is to access the kinematics, which was not really possible with FUSE. You want to study in detail the width and the centroid of the O6 lines and the different components. Then you get a lot of metal lines, especially from the H1 region. So here I noted some of them, not all of them. And so what you can do here is to measure chemical abundances because you have the hydrogen reference as well. But you can also calculate cooling rates. So you have C2 star and you have silicon 2 star. So it corresponds to the fine structure level of ionized silicon. And so you can indirectly study heating mechanisms and so on. Because you have all these metals, you can also study depletion patterns and try to infer the dust content and composition. So there are a lot of papers on the topic. And maybe what's an issue, especially for extragalactic studies, is the lack of spatial and spectral resolution. So you really want to access, to have the highest spatial resolution possible. And I will come back to it in the next slide. For the circumgalactic medium, you can study the infall rate of the gas in the Milky Way, but you can also do that in other galaxies, although it's very difficult, but with LUVOIR, it will become easier. And what's important to notice here is that these high velocity clads and intermediate velocity clads, they They are multi-phase and they have metals, so you can you need and you can use tracers like a silicon 2, 3, 4 in order to probe the content of this clad and eventually measure maybe an inflow rate. So based on everything I just said, what has been missing is really a high spectral resolution. It's really important to resolve the velocity components. And if you think of a cold gas, the line width typically are going to be around 2 or so kilometers per second, which means you need a resolution of 10 to the 5 or more even, if possible. So here you have an illustration of the difference of a spectrum with 20,000 and 90,000 for CO transitions. You can see the dramatic change. It's really important if you want to measure reliable column densities. Here is another comparison with HST GHRS, which had a high spectral resolution, and FUSE, which was lower. So LUVOIR really improves on all the important requirements because it gives access again to the far UV range with a high spectral resolution and a very large effective areas. But like I said, below 1,000 angstrom will, if LUVOIR stays the same, remain invisible. Now you want to access the kinematics as well. So through the high spectral resolution, for instance, so there were some results showing that there was an increase in the H2 velocity dispersion with the rotational level, and that was interpreted as H2 formation in a post-shock zone through the H- path, sorry, in a partially ionized gas with this pretty warm temperature. That was really possible because you have access to the spectral resolution in order to do such a thing. Then there is also the CH plus formation, which is endothermic, that can be through, using H2, warm H2 out of equilibrium. And the one problem here is that the model still underpredict the higher rotational levels. And so one explanation could be dissipation of turbulence, but that remains to be confirmed. And so it's important here to have a high spectral resolution to examine the profiles in detail, but also compare H2CO and CH+. Okay, so polarization. So it's a brand new field in the UV. So it's kind of unexplored territory and a huge discovery space potentially. So as you all know, of course, this polarization was available with, well, for instance, Planck, but the spatial scales were large and the polarization was integrated along the line of sight, or maybe diluted, I should say. And if you study the gas polarization, you can access to small spatial scales, especially in the UV. You can access different ISM phases because you have all these tracers, and you have the 3D structure through the spectral resolution, which can reach 10 to the 5 then with polyps. And so here we're talking about polarization, which is linear polarization. Due to the alignment of the angular momentum of these atoms, which are all in ground state. Actually, I should have said, but most of the transitions I was talking about are resonant transitions. And it's very sensitive, it's sensitive to very weak magnetic field. And that alignment is produced from the anisotropy of local interstellar radiation field or a star in the vicinity. So for instance, in the bottom here, there's a star on the left here somewhere. And you have the polarization fraction showing, and that's about 1 parsec by 1 parsec with a 3 microgauss magnetic field. But it's completely unexplored in the far UV, but it's very interesting because potentially you can study the role of magnetic field in the distribution of the ISM phases, the role of magnetic field in circumstellar disks where infrared millimeter observations can be tricky to interpret. I'm not saying it's going to be easier here, but it can provide another point of view at least, or the accretion of gas in star-forming filaments. Now, if you have the sensitivity, you can access very faint lines and scarce elements, and it's important because so if you access all these metal lines, you can, like I said, try to infer the dust composition and the dust depletion. And if you do that extremely accurately, then you can measure precise and accurate elemental abundances. to the point that you can start seeing things like this new result of Nadesia. She measured several lines of sight. She tried to do the best job possible to measure the depletion toward different lines of sight in the Milky Way to get the accurate, well, the most precise abundances possible. And she saw large variations of the metallicity on 10 parsec scales, including 17% solar metallicity lines of sight. So the interpretation here is that there is low metallicity accreting gas, but it doesn't efficiently mix into the ISM. And in the bottom figure, you can see this result. 0 is the solar value, and see you have a bunch of lines of sight with metallicities that are much lower actually. And the average, if I'm not mistaken, is about 0.5 solar, not solar. So it's pretty interesting, and you can potentially, with LUVOIR, do that in more details and in other environments, potentially in other galaxies as well. So it becomes extremely powerful. And talking about nearby galaxies, one interesting prospect in the UV is to transpose the level of details that we have currently for the Milky Way, which is already pretty good if you compare to what we know in nearby galaxies, to transpose that level of details to the nearby galaxies. And why is that important? It's because you don't need to go very far to have extreme environments. We can talk about low metallicity, but also different chemistry, different dust composition, different dust contents. And so in the bottom plot, it's showing a metallicity versus distance for a selection of sources, but basically you can go to 1 megaparsec or just above, and you will reach metallicities close to 2-3% solar already. So it becomes really interesting to do ISM physics with these metallicities. The trick here is that if you don't have the spatial resolution, all you see are stellar clusters that are unresolved. And it's a biased study in a way, because you have a lot of nonlinear effects, because you have different stars, they have different brightnesses. Each line of sight intersects clouds that have different properties. At the end, all you see is one line, and you measure column density. And so it's very difficult to interpret that. So you need spatial resolution in order to see these individual stars in the galaxies, and you need the sensitivity, of course, to detect that continuum. And that's probably because of this challenge that there's still this ongoing debate. I'm not going to talk about it too much here, but there's this ongoing debate about potential metal deficiency in the H1 region of blue compact dwarf galaxies as compared to the H2 regions, where it's measured with the INAS gas. And so the systematic biases that we have because of the effect I mentioned in the previous slide are really hampering us to reach a full conclusion here. But I will go quickly here and maybe mention more the star forming gas reservoir at low metallicity or not, but at low metallicity, what's interesting is that in blue compact dwarf galaxies, the molecular gas fraction in the diffuse ISM is ridiculously low, but that's explained by enhanced photodissociation. Models explain it pretty well. But what's interesting is that you do measure, you do detect warm H2 in the near infrared. And so that means that H2 must exist in small dense clumps that are on parsec sizes or even less. And ALMA started to see these in CO. So that's a picture of WLM galaxy of 1/8 solar metallicity. But if you go below 1/8 or 1/10 solar metallicity, then CO is pretty much hopeless. And so you still need, and if you still want to investigate the H2 clump size and mass distribution, you can do it in the near infrared, but you will see probably just the warm outer layers of these clouds. And in the far UV, if you can reach high enough AV, you can probe the molecular content of these molecular clouds. At least that's the idea. Okay, and then, so you, like I said, you access some fine structure lines. So it's in absorption, with which you can measure the cooling rate and physical conditions in the neutral gas, warm neutral or cold neutral medium, which is relevant for future star formation episodes for the extragalactic science. It gives you also indirect constraints on gas heating mechanisms, photoelectric effect heating, which we talked about this morning, or photoionization by far UV or X-rays. And these fine structure lines in absorption, they've been already observed in the far UV in the Milky Way, in the Dampleman alpha system, and a few blue compact dwarf galaxies, but it remains pretty difficult to do. But with LUVOIR, we can really expect that these lines like C2 star, but also silicon 2 star, O1 star, 1 star star, which is which corresponds to the second fine structure level of O1, will be much more frequent. And here, maybe it's an important note also is that so of course you get line like C2 in the infrared, but it's difficult to get a spatial resolution for this wavelength. While here you get C2 star toward one line of sight. So depending on your observation, you can reach a high spatial resolution, which could be interesting for some cases. Yeah. Okay, I'll skip that. And so actually, I'm almost done. So here it's a usual sketch that shows that you can do a tomography of the intergalactic medium using quasars as background sources. So you all know that's the Lyman alpha forest. And you can think of LUVOIR as a way to do that, but instead of the quasars, you have stars in the Milky Way or in an external galaxy. And what you're doing the tomography of is the interstellar medium of that galaxy or of the Milky Way. And if you add on top of that potential polarization, you can see it becomes really, really powerful instrument. And so to summarize, you need a high spectral resolution to disentangle the ISM components, because as you saw, there are a lot of tracers in finally a pretty small wavelength range when you think of it. You need to resolve the clouds and study the kinematics. Accessing faint lines is actually also very important. And you need spatial resolution to probe individual lines of sight in galaxies that are more distant than the Magellanic Clouds, which is pretty much the limit what we can do right now. Individual lines of sight toward the LMC or SMC, it's possible. It's being done with HST. But if you go much further, well, if you go a little bit further than that, it becomes too difficult. And also a lot of the tracers are around 1100, I mean, yeah, below 1100 angstroms and sometimes below 1000 angstroms. So that part of the spectrum is also important to consider. And so here I listed some the requirements. It's for Pollux. So what are the requirements and ideally what we would like to reach? I didn't mention, but Pollux is a linear and circular polarization as well. And just to conclude, so LUVOIR being a multi-wavelength telescope, there are a lot of synergies within LUVOIR. So you can think of pre-selecting far UV bright stars with the imager, or mapping, do a spectroscopic mapping with LUMOS, and then follow up with high spectral resolution and polarization with Pollux. Then you have all the optical spectrum as well, potentially. So you can do a multi-phase study of the neutral and ionized gas. You can do extinction measurements, and you have the near-infrared tracers for shocks or H2, for instance. And I listed some synergies with other observatories, but there are much more than that. And finally, yeah, this last point is because I didn't have time to mention everything. So you could also, for instance, the second one is interesting for the XCO factor. You can calibrate by measuring CO and H2 in absorption, the CO over H2 calibration, even as a function of AV, which is really interesting. Yeah. And that's it. Thank you.
So we have a few questions. Quentin Salomé first.
Hi, yes. First, thank you for your very interesting talk. My question is about Pollux. Maybe I didn't catch the message, but why do you only focus on the 15 meters version of LUVOIR for Pollux? And do you have some like backup or other alternative in case LUVOIR is not accepted, for instance, on the EUVU?
Right. Yeah. So it's a very good question, and I'm sorry I should have mentioned it. So Pollux is proposed only for the 15-meter version only, and I think it's just a matter of room on the focal plane, because it would be too difficult to put the 4 instruments on an 8-meter version of LUVOIR. I hope I'm not wrong on that. And then the second question: is there a backup plan? Well, as you saw, Jean-Claude Bourret and Coraline Henner are also no eyes on the proposition for the EUVO. And so I would imagine that if Pollux, well, if LUVOIR 15 meter is not selected and so Pollux is not selected, then there would be a backup plan to use something like Pollux in the EUVO, because polarization, for instance, is one of the things that are advocated for the EUVO as well, if I'm not mistaken. So I think that's the idea.
Okay, thanks.
Thank you. Jérôme, you have a question too?
Yes, about the tomography of the ISM, did you make any computation about the number of stars that would be interesting to do a fair fraction of local ISMs, for instance?
That's a very good question. No, I didn't. And that would be something more relevant for LUMOS, I think, the multi-object spectrograph, than Pollux, which is really focusing on one point source in detail and spending a lot of time on that source. So I don't think Pollux is necessarily adapted to making many observations of different sightlines in one given area, even if it's to reconstruct after the distribution. I don't think so. LUMOS could do that. So the spectral resolution is 30,000. And I'm not aware in the final report of LUVOIR of a simulation that would do something like that, actually. And maybe it's because the ISM is not one of the science pillars of LUVOIR, unfortunately.
Okay, so maybe I have a last question. You mentioned some molecular species, carbon species. What about the diffuse interstellar bands? This was not in your talk. Can it be used to study that? I guess in the UV and visible range.
I guess you could, but I don't know what LUVOIR brings that other observatories wouldn't do already. So
okay.
On top of that, I'm not an expert on that. So maybe there are some people here who can answer better than me, I'm sure.
Yeah, okay. So thanks.